Hello and thank you for watching this video presentation of our paper, Microsecond Consensus for Microsecond Applications. My name is Igor, and this is joint work with Marcos and Naama from VMware, with Rachid and Athanasios from EPFL, and with Virendra from Oracle. Broadly speaking, our paper revisits the question of whether consensus has to be slow. Folklore would dictate that consensus must come with a prohibitively high overhead and therefore should be avoided, especially by performance-conscious applications. However, through this work, we show that this need not be the case. In fact, we show that with the right technology and with the right algorithms, it is possible to achieve consensus within nearly microsecond latency. But why should we even care about microsecond consensus? Well, microsecond consensus is relevant if you want to replicate microsecond applications. There are many microsecond applications emerging across various fields. In finance, for instance, with high-frequency trading, in embedded systems with industrial robots, and somewhat closer to home, in microservices. Among these many microsecond apps, some of them can benefit from replication. For instance, if they hold crucial state that needs to always be available. But of course, if you are replicating a microsecond application, the replication itself should also be at the microsecond level. Otherwise, the replication would negate the performance benefits of having a microsecond app in the first place. There are many replication solutions out there, but none of them are fast enough for this use case. Any replication solution that relies on TCP/IP has to be ruled out from the beginning because the TCP/IP stack itself adds an overhead of at least 100 microseconds. Of course, there are faster RDMA-based solutions, but even these are not fast enough for this use case. So through this work, we show that if you combine the fastest technology available, namely RDMA, with good algorithmic design, then you can get close to this microsecond replication. This brings me to our contribution, which is called Mu for micro. Mu is a state machine replication system designed to work in fast networks such as those you can find in a data center. In the common case, when there are no failures and there is no asynchrony, Mu is able to replicate small requests in just 1.3 microseconds. And this is 61% faster than the state of the art. In the less common case, when the leader is slow or has failed, Mu is able to fail over to a new leader in under 1 millisecond, which is 90% better than the state of the art. So for the rest of the talk, my goal is to give you the intuition behind our design, which allowed Mu to have such low common case replication time and such fast failover. So the outline for the rest of the talk is as follows. First, a couple of background slides on RDMA and state machine replication. Then we'll see the two questions regarding replication time and failover time. And finally, a glimpse at our evaluation. So RDMA stands for Remote Direct Memory Access, and it is a feature of networking hardware which allows a server to directly access, meaning read or write, into the memory of a remote server without involving the CPU at the remote server and without involving the operating system at either side. Due to its kernel bypass and due to implementing several layers of the communication stack in hardware, RDMA typically delivers very good performance with latencies around 1 microsecond and bandwidth in the hundreds of gigabits per second. A crucial detail regarding RDMA, which we rely on in our work, is that it provides configurable access permissions. What this means, to see what this means, consider the example earlier where server 1 has read-write access to the memory of server 2. Server 2 has the ability to change these permissions dynamically during execution. So it can at some point decide to revoke the write access of server 1 and grant write access to another server. And this will come into play later in the talk. My second background slide is about state machine replication. This is the level of replication that we are targeting with this work. State machine replication allows us to replicate a service across several machines or replicas to provide availability and consistency despite some of these replicas possibly failing. State machine replication is different from other forms of replication by the level of consistency it provides. So this level is called strong consistency or linearizability. Intuitively, what this means is that even though the service is implemented across several replicas which may fail, the service behaves indistinguishably from one which is implemented on a single replica which never fails. A common approach to state machine replication, which we also adopt in our work, is as follows. Every replica has a copy of the application as well as a consensus engine. And the replicas use their consensus engines to agree on a total order for incoming application requests, after which these requests can be applied to the local copies of the application. And of course, if one of these replicas fails by crashing, then the other replicas have enough information to continue providing the service without the crashed replica. Let's tackle the first question. How does mu achieve its near microsecond replication latency? To answer this question, let's see first how replicas are organized in mu at a high level. This is the same picture as before, but I'm just showing two of the replicas, and I have enlarged the consensus engine box to make room for some components that will appear later. So in mu, a replica can take one of two roles, either a leader or a follower role. These roles are not static, so a replica can switch between these roles during execution. In the common case, there is only one leader, but we do not enforce this invariant in the protocol itself. So if it is possible in rare cases that several replicas consider themselves to be leader, and the protocol tolerates this situation without breaking safety. So a leader replica is responsible for communicating with the clients, accepting application requests, and then replicating those requests using the consensus engine onto the followers. After a request has been replicated, a leader will apply it to its local copy of the application and then respond to the client. Followers do not interact with clients and instead passively wait for the leader to replicate requests inside their consensus engine. And afterwards, they apply these requests to their local copies of the application. Followers also monitor the health of the leader, and if the leader has failed or is slow, they are prepared to take over as leader. Let's now examine the lifecycle of a request inside mu, in the common case. So let's say the client has a new request, which it sends over to the leader replica. The request is then captured and sent to the consensus engine, where it is appended to the consensus log of the leader. The next step is replicating this new request from the leader's log onto the follower's logs. And this is the step that we want to make as fast as possible. So in order to accelerate this step, we want to minimize the amount of communication between the leader and the followers. So the minimum possible amount of communication is a single round trip. So this is exactly what we do in mu. To replicate this new request onto the followers, the leader will issue RDMA writes in parallel from its log onto the logs of the followers, and then wait for low-level RDMA work completions or acknowledgements that these writes have completed. And so the leader waits for a majority of these acknowledgements to arrive. And it's important to note that these acknowledgements do not contain any protocol-specific information. They are low-level acknowledgements which just indicate that the write or writes have succeeded. So to go back to this question, how does mu achieve its near microsecond replication time? The answer is that mu replicates requests in a single round trip in the common case. And this is done by the leader simply writing onto the follower's logs. At this point, if you're familiar with consensus protocols, you may be wondering why it is safe to decide after a single RDMA write, especially given that I've told you that there can be several competing leader replicas at any given time. So the answer is that we rely on these configurable RDMA permissions that I mentioned earlier to ensure safety. And I have a couple of slides to explain the intuition behind that. So in Mu, we maintain the invariant that only one replica has write access to the memory of every given server. So let's see how that plays out in this time diagram. So here time flows from left to right, and we have 3 servers or replicas. Here, server 1 and 3 consider themselves to be leader, and server 2 is a follower, but its memory is being used for replication. So server 1, before it's able to write on the memory of server 2, we will ask for permission, and that permission is granted, and then can write on server 2's memory. Now, server 3 wants to write on server 2's memory, and it will ask for permission first, which it gets. And at this point, server 3 has stolen the permission of server 1 because of the invariant. So if server 3 gets permission, server 1 must lose permission. And so later, when server 1 tries to write again, this write will fail because server 1 has lost permission. So at this point, server 1 knows that there is a competing leader who has stolen its permission. If, however, server 1 is fast enough and manages to get this second write in before server 3 comes to steal its permission, then when the write succeeds, server 1 knows that it has been running solo it has been the only writer on server 2's memory since the initial point in time when server 1 got permission. So this is enough information to decide at the end of the write, because it not only knows that the write has been successful, but it also knows that no other leaders wrote on this follower. And so we add a small and very simple permission management module to the consensus engine to handle these permission requests and switch permission over from one leader to another. Let's now move on to the second question. How does Mu achieve its sub-millisecond failover time? Well, any failover mechanism must include a failure detection phase. And our aim is to make this failure detection phase as fast as possible and therefore reduce the overall failover time. So let's see how we do that. I've brought back the same slide, and now I have added this failure detection mechanism here. So our failure detection mechanism is heartbeat based, but unlike other failure detection mechanisms, it is a pool score based failure detection. What does this mean? Well, pool means that instead of sending out heartbeats to the other replicas, replicas instead have a local heartbeat, which is a counter that each replica continually increments, and then they pull or read using RDMA the heartbeats of other remote replicas. And based on the values inside these reads, each replica will assign a badness score to every other replica, and this badness score reflects the level of suspicion that this replica has that the other replica has failed. So if I am a replica and I see the same heartbeat value over and over as I'm reading the other replica's heartbeat, then this is evidence that the replica has failed because it's not incrementing its heartbeat. So I increase its badness score. If, on the other hand, I see increasing values of the heartbeat, then this is evidence that the replica is alive and well, and so I will decrease its score. And as you might expect, there is a threshold above which I consider the other replica to have failed. And what's important to note here is that the score is not affected by the slow reads. So if there are fluctuations in network time, this might cause a read of a heartbeat to be slow, but this will not cause me to falsely suspect the other replica, because what matters is the value inside that read and not if it arrives slightly earlier or slightly later. So this allows us to completely discount common network fluctuations when setting the threshold, the failure threshold. So to come back to the question, how does Mu achieve its sub-millisecond failover time? The answer is because of this pool score mechanism, which is impervious to net fluctuations in network latency, we are able to have a very aggressive timeout or an aggressive failure threshold, and therefore have very fast failure detection. Let's now move on to the last part of the talk, which is the evaluation. So before I show you the results, let me set up talk to you about the setup of our evaluation. So we wanted to measure several metrics: latency, the replication latency, the failover time, and throughput. But due to limited time, I will focus only on the first two in this talk. We evaluated mu by replicating several applications: an RDMA-based key value store called Herd, a financial application called Liquibook. So Liquibook is an order matching engine, and its job is essentially to receive, buy, and sell orders and match them as best as well as possible. And finally, we also replicated TCP/IP-based key value stores, Redis and Memcached. We compared against other RDMA-based replication systems, DARE, APUS, and Hermes. Now, ideally, we would have used all of these replication solutions to replicate all of the target applications, but they are not all compatible. So I have this graph, I have this table here to explain which replication solution is compatible with which application. So mu is compatible with all of them. DARE and Hermes come with their own replicated key value store, and so we cannot, as far as we know, we cannot untangle the replication from the key value store and easily apply that replication to other applications. So we just compare directly against their built-in key value stores. And APUS is able only to replicate socket-based programs, and therefore we compare against it for Memcached and Redis. Here is our hardware setup. We have 4 servers connected via 100 gigabit per second InfiniBand. And so since we have 4 servers, we will test with 3-way replication and reserve one of the servers for the client or clients. This first graph shows replication latency. So this is the time that a request spends inside the consensus engine itself. So the first 4 bars show the replication latency of mu with Herd, Liquibook, Memcached, and Redis. And the next 4 bars show the replication latencies of DARE, Hermes, and then APUS when replicating Memcached and APUS when replicating Redis. So the takeaway from this graph is quite simple. Mu is able to consistently outperform the competing solutions by 3 to 4 times, and mu is able to achieve nearly 1 microsecond replication for a variety of target applications. The next graph shows failover time. So, like I said, failover time, a large part of failover time is failure detection, and another important component is the permission switch time. So after the new leader has detected that the old leader has failed, it needs to request permissions from its followers so that it can start replicating on them. And this permission switch time is mandated by the hardware because switching permissions is a low-level RDMA command. So we have here 2 histograms. The one on the right shows the total failover time in microseconds. So we can see that the failover time remains below 1 millisecond. And the histogram on the left shows the permission switch time. And we can see that the permission switch time is non-negligible. It's around 1/4 of the failover time. So this can serve as incentive for hardware manufacturers or driver designers to try to reduce this permission switch time and therefore have more responsive systems. Okay, this brings me to the conclusion. In this talk, we have shown that near microsecond consensus is possible, and this is great news for those microsecond applications which can benefit from replication. We have introduced mu, an RDMA-based state machine replication system, which has very low replication time due to its single round-trip design, and has sub-millisecond failover time due to its aggressive pool score failure detection mechanism. We have made the code of new available at this address, and I invite you to check out our paper for more details and more experiments. Thank you very much for your attention.